So we want to find the power series for this function and then figure out for what x values with the power series. So the interval convergence just means for what x values would that power series be valid for that function, okay? So x over okay, so we could rewrite this as x over 1 minus negative 2x squared, and now it looks just like the sum of our geometric series, right? So a equals and r equals negative 2x squared. Okay, so we can set up then the power series is going to be n equals 0 to infinity. A is x times negative 2x squared to the n.
Can you pull x out of it?
Yeah, so if we want, we can combine the x's. So really we have, and this is something we'll be doing a lot of today. So how many x's do we have? This is x to the what? And if you combine these, you have x to the 2n, and then times another x. So this is x to the 2n plus 1 is what we really have. And then this is negative 2 to the n. So is that it for the power series? And then you should be very, very comfortable if you were to have to write out what are the first 4 terms or what are the first 5 terms. You should be able to do that. Okay, that should be a piece of cake. Because we look at this, we see this, and we think what, right? We see a series like this, and we think, what do we think?
Summing a bunch of terms.
Yeah, we're summing up a bunch of terms. Each one of those terms looks like this, with a different value of n, right? Starting with 0, then 1, then 2, then 3. Okay, so plugging in different values of n and showing, say, the first 4 or 5 terms. WebWork has you do that a lot. They'll have you do a series, but then instead they'll say, okay, what are the first 5 coefficients, or what are the first 5 terms? So that's really important because it means you understand what this means. Okay, and so now we want the interval of convergence. So the interval of convergence is going to come from the limit ratio test, right? So we're going to do limit as n goes to infinity of, here we go, negative 2 to the n plus 1 times x to the 2n plus 1 plus 1. Since we don't have a ratio here to start with, I'll just make a ratio over negative 2 to the n. Okay, so I think we'll have one more negative 2 in the top. And then we'll have how many more x's in the top? What is this? This is 2n plus what?
1x.
No, this exponent here is 2n plus 3, right? 2 times 1 plus another 1. So it'll be 2n plus 3, and then this is 2n plus 1. So how many more x's do I have in the top than the bottom? 2. Okay, and so as n goes to infinity, we just get this, right? There's no n's in there. So this doesn't care about what n does. So basically we have that negative 2x squared has to be less than 1. Or 2x squared less than 1 greater than negative 1. So I think x is going to be less than, what, square root of 1/2? Negative square root of 1/2? Is this right? But because we have this alternating, we saw this in class, we have the alternating effect on the series, we're going to plug in this endpoint and this endpoint and see if either of them give a convergent series or not. Okay? So we'll start with x equals negative square root of 1/2. And what will we get for that? Negative 2 to the n times negative square root of 1/2 to the 2n plus 1. Okay, so if we're going to simplify this, then we could take 2n of these and then multiply it by 1 more of these. So you could rewrite it this way. Is that fair, like that? And then, this is kind of ugly here. Okay, so what do we have? We have okay, so we have negative 2 times, so we could bring the square here inside and then combine this whole thing. So we're going to have negative 2 times this thing squared, which would be positive 1/2, and that all to the n. But then times another negative square root of 1/2. And so what does this? This is just then negative 1 to the n. Of this. Well, that's alternating, so that can't, alternating, and it's just the same value over and over again. So this is negative 1 to the n times negative, so that's definitely divergent, because basically you're just doing negative radical half plus positive radical half, negative radical half, positive radical half, right? So your terms are just alternating between radical half and negative radical half, and then it's just gonna be this. This is what your series is going to look like. On and on and on. Will that converge? No, it's just going to keep going back and forth between negative radical half and 0. Negative radical half. And then when you add this, you'll get 0. And then negative radical half. And you add, you get back to 0. So you're just going to keep flip-flopping back and forth as you keep adding terms. You're not going to converge on a value. So that's divergent. So we want to keep this strictly less than. So I'm not, so then when it's positive, what's the difference? This is still the same, and this is positive. Right? So if I did x to the positive square root of 1/2, then this is going to be positive right here, but I'm going to square it when I move it into the n, so this is going to be the same. I'm still going to get negative 1 to the n, but then over here it's going to be positive. It's going to do the same thing. So when x is positive square root of 1/2, I get this. And that also just flip-flops back and forth. Square root of 1/2 minus square root of 1/2. Square root of 1/2 plus minus square root of 1/2. Just flip-flops, so it doesn't converge. So neither of the endpoints make it convergent. So this is the interval. So, and then better form is to say negative radical 2 over 2. Final answer. Okay, did that help? Did it make sense? That's the same. This is just 1 over square root of 2. So if you rationalize the denominator, it's radical 2 over 2. I just rationalize the denominator. 1 over the square root of 2, which is the same as this, is equal to square root of 2 over 2. Did it help? Any questions? Please.
I think I have 2 questions. So for when you're finding the intervals of convergence there,
Mhm.
is it wrong to take from where when you first wrote the series in the a times r to the n form, to just because you can see the r is equal to negative 2x squared,
Mhm.
and just set that in between negative 1 and 1?
Yeah, that's what I was gonna say.
Yeah, exactly. Because this is exact. Yeah, totally. So you don't need this.
Okay.
You don't need actually. You don't need limit. If you've got what do you have? You have this geometric, and for the geometric to converge, r has to be between 1 and negative 1. There it is, right there, or down here. Yes, you could just go right from this and start there. That's absolutely right.
Okay. And then, so if you were to say like we had to write out the first like 4 or 5 terms in the series, so would you just go subbing in n equals 0, n equals 1, n equals 2, or do we have to look at the power of x, where that would be like c sub, like n equals 0, there would be c sub 1, that puts x to the power of 1.
Okay, well, so if you just wanted the 5 terms, then all you would need to do is put in 0, 1, 2, 3, 4. But if you need to, if it has to be in this form, Cn x to the n, then we have some work to do.
Okay.
And in fact, I don't know. Yeah, if you have it in this form, then you have to kind of write out the terms of this and write out the terms of this and figure out where you're going to need zeros. Some of these Cn are going to be zeros because you're not going to have x to the first, second, third. You're going to have what? This is going to skip by 2's. So you're going to have every other one of these is going to be a 0 if you need it in this, if you need the coefficients from this form. Because you're going to have what? 0. This is going to be all the odd powers. X to the first, third, fifth. So then all your even coefficients will be 0 from this form. Does that make sense?
Yeah.
Okay. Other questions? All right, let's hand in the written homework. So I need name and date. What's the date? 18th? Name and the 18th, please. Please give me a clean left edge. Is that all of them? Okay, so let's look at something like this. Make that 3. So we want to find a power series for this. 3 over quantity 1 minus x cubed squared. No, we don't. Let's see. I need to change that. Let's see. Let's just do 1 minus x. Okay, so does this fit the form that for power series or for geometric series we can use a over 1 minus r? Okay, no, it doesn't. Okay, so we need something else. So this doesn't fit the a over 1 minus r form, but it's kind of one function away from that. How is it one function away from a over 1 minus r? What's that? Okay.
And then write the geometric series 1 over 1 minus x squared.
So the problem here is like the denominator would be 1 minus 2x minus x squared, right? And that doesn't fit the geometric form 1 minus r. And we don't want to make this whole thing r. That won't be good. So how is this function? It's kind of one function away. In what sense is it one function away from our geometric form? Square root. Okay, square root, but then we'd have to square the thing that we got, and we don't want to square an infinite series, right? Like the whole sum, trying to square it, that's not going to work. Yeah.
Maybe we multiply by the same, like 1 over 1 minus x.
Oh, so again, then you're going to have two you can have two infinite series that you're multiplying together in the end, and that's not going to be good. Martin, what were you going to say?
I would say like almost the same. Like if you multiply 3 to 1 minus x, you can make it 1.
Okay, so it's not just a matter of multiplying or something like this. So what this really is look at what would happen if we took the antiderivative of this. What would the antiderivative of this be? 3 over 1 minus x, right? And I think, is that it? So therefore the derivative of 3 over 1 minus x is the function we have. So just to check that, we've got 3 times 1 minus x to the minus 1, right? Derivative would be negative 3, 1 minus x to the minus 2 times negative 1. And that equals 3 over 1 minus x squared, right? Does it make sense? So what about 3 over 1 minus x? Can we do that?
Yeah.
So we can do that. We can do 3 over 1 minus x, and then if we have the power series for that, what can we do to get the power series for ours? Take the derivative of it, you see? So we could find the power series for 3 over 1 minus x, which is easy. So 3 over 1 minus x is the sum as n goes to 0 and 0 to infinity of 3 times x to the n. And let's write out some terms here. So it'd be 3 plus 3x plus 3x squared plus 3x cubed, etc. So then we know that the derivative of 3 over 3 minus x is the one that we have. So we can just take the derivative. So what is the derivative of this polynomial? So it would be 0 plus 3 plus 6x plus 9x squared. So the next one would be 3x to the fourth, so what would that be? 12x cubed? This is equal, not arrow. And this is equal to, okay? But only for certain x. So what x's would this be true for? What values of x does this function equal this power series function? Negative 1 to 1, right? So here's your r value, is your x. So only from x between negative 1 and 1 will this infinite polynomial match up with this rational function. It'll be the same. Okay, and so we want the derivative of this, and so we can see the derivative of a polynomial is easy, and we just did it. So now the question is, what is this? Well, we can take the derivative just of a general term. So what is the derivative of 3x to the n? 3n x to the n minus 1. But when you do that, you have to adjust your index. What is going to be our starting n value so that our first term is 0? What will be? So when you take the derivative of the general term of the series, yes, you just follow the rule just like a normal derivative rule, but then now you're starting at n equals 1 instead of n equals 0. Because n equals 1 will give us that 0 that we need. N equals 2, then will be this 3 here.
Will n equals 1 give us 3 for the first one?
Oh, you're right. So we know, what do we want? 0. How do we get 0? Oh, it's still 0 in this case. Is that right?
Oh, yeah. 0.
Yeah, n equals 1 gives us, right, exactly. So we weren't careful enough. N equals 1 gives us that 3. So it's still correct. We could start at 1, and we'd still get the same thing because we're adding 0. So in this particular case, n could start at 0 or 1. It doesn't matter. So we would just want to watch for that. We're just going to watch and see, do we need to start n equal to 1? So just look at the individual terms and see what you're going to need if you're going to try to write the derivative this way. But if you don't need this form of it, the summation form, and you have the polynomial, the power series, just take the derivative, and there's your power series for the derivative. Okay, if we wanted then to adjust this and actually have it start at 0, then it would be 3 times what? N plus 1. You see that? So when n is 1, now n is 0, so this needs to be n, and it'd be x to the n. So this would be if we wanted to write it in the form n equals 0 to infinity, Cn x to the n. We just did it. Okay. Okay, so why don't you try And let me do another example, and then we'll give you one. Okay, questions on this example? So let's try this. F of x equals x over 1 plus 2x squared. Okay, so we're going to do the same thing. We want to look at what could we get a power series for? So what about this x? Is this helping us out if we want to get the antiderivative of this? It's not really helping us out, right? So, but what we can do is we can just do this. And once we have the power series that we want for this, for the antiderivative of this, then we can just multiply by x. Okay? So let's just follow. Let me just do it and you can see what happens. Okay, so what is the antiderivative of 1 over 1 plus 2x squared? So we're going to have 1 plus 2x. And then what are we going to need in the top? So when we take the derivative, we get this thing. Well, when we take the derivative, we're going to have a 2, right? So we need a 1/2, but then we're also going to have a negative. We're going to need negative 1/2. So let's just check that. So the derivative, take the derivative. It's going to be negative 1/2 times negative 1 to the 1 plus 2x to the negative 2, right? Times 2. And so we got negative 1 times negative 1/2 times 2 is 1 all over 1 plus 2x quantity squared. So is my antiderivative correct? Okay, so this means that the derivative of negative 1/2 over 1 plus 2x equals 1 over 1 plus 2x quantity squared. So here's what we're going to do. We're going to take the power series for this one first, and then we'll do the derivative of it, and we'll have the power series for that, and then we'll take that power series and we'll multiply it by x, and we'll have the power series for this. Does that make sense? Okay, so we want the power series for negative 1/2 over 1 plus 2x. It's going to be negative 1/2 times negative 2x to the n. That should be easy. We could write out some terms here. So it's going to be negative 1/2. N equals 1. Is that just x to the 1? N equals 2. It's going to be negative. Let's simplify that. Hold on a sec. Let's simplify this thing first. I think that'll make it easier. So this is negative 1/2 times negative 2 to the n times x to the n. So really, we have negative 1/2 times negative 2 to the n times x to the n. I think that'll make our life a little easier in terms of writing out some terms. So 0, it's going to be negative 1/2 plus when it's 1, it's going to be, this will be positive 1 times x to the 1, so it'll be x. And then when it's 2, that'll be 4 divided by 2, negative 2 is negative 2x squared. Do one more term. When n is 3, it's going to be negative 8 times negative a half is plus 4x cubed. Agree with that? Sorry, that's hard to read. So negative a half plus x minus 2x squared plus 4x cubed, etc. Agree? Okay, so then what we say? We're going to take the derivative. We're going to take the derivative of everything, and when we take the derivative, we're going to get this. And then all we need to do with that power series is multiply it by x. And we'll have the power series for x over 1 plus 2x quantity squared. Okay, so the derivative we know is a 1 over 1 plus 2x quantity squared. And that equals, so what is the derivative of this with respect to x? Let's hold off on the n. So it's just, this is gonna all just come along for the ride. And then we're gonna have what? Times n x to the n minus 1. And that will be, what, 0 plus 1, taking the derivative, minus 4x plus 12x squared. And then starting, if we do it starting at 1 like we did last time, the first term we get is this 1. Okay? And then we get the minus 4x and the plus 12x squared starting from 1. So now to get this function, so f of x is x over 1 plus 2x squared. It's just going to be this thing times x. So what will it be? N equals 1 to infinity, negative 1/2, negative 2 to the n times what? X to the? We're just going to multiply by x, so we get x to the n. And it's going to be 0 plus x minus 4x squared plus 12x cubed. And there it is. Okay, now if we want, so what are we going to do now? If we want this in the form of Cn x to the n, starting at n equals 0, what will we do? So if we wanted to get this in the form Cn x to the n, starting at n equals 0, how are we going to change this so we preserve? So we already have it x to the n. So if we just change this to 0, does it still work? Does it still give us the same series, same sum of terms? So now start at n equals 0 instead. Do we get the 0 for first term? Yes, because of the n equals 0 right there. And then when n equals 1, we get our x, and etc. So if you wanted to get it into this form, like on WebWork, they have to do that, then all you have to do in this one is just change that to a 0, and you get the same. The question is, do you get the same terms or not? You want to be able to generate the same terms. That's what dictates how you can adjust these, like adjust the index. So it's okay on this one, change it to 0, and then all it does is gives you that 0 when n equals 0, and then when n equals 1, it starts off right there. And now this thing is in this form, our general power series form. Okay, I'm doing a lot of talking. Any questions?
before we switched to the power series form and we set n equals 0,
Uh-huh.
if we start at n equals 1, that's 0, right?
That's right, but then that doesn't change it because it's a 0.
Right.
You see, so it's okay. It works either way because if you skip n equals 0, then you're skipping adding 0. It doesn't change the value. Yeah. But the key is if you're trying to adjust the index, find your terms that you know the terms are right, and then look at adjusting the index. What's going to give me the exact same terms? How would I change the series but still get the exact same terms? That's the key that you're going to get on the right there. Those same exact terms added together. Okay, so let me see how you do on something similar but different. How about this? Okay, so it's a similar principle, but this one's different. So you got to think about how is this or part of this one step away from something that we could construct a power series for based on a geometric series. Okay, so put your heads together. I'm going to give you sheets for this.
Right.
Nothing derives to LM.
Right.
Oh, making it too hard. This is your goal. This is your goal. Goal is A over 1 minus R.
That makes sense. That would be like a perfect.
Start doing your notes first.
Yeah.
Pull that off. Put that on later.
Like we did on that one.
Okay. Is that derivative of right? Which is? Right. Minus 2x. Okay. Right, and then that will be in that form, and so then you can do that power series, and then do what's that power series to get this?
You pull out the negative 2x.
Another.
You do the derivative of that, being the power series of the derivative of that, and then you want the power series of that, and it's an antiderivative.
X squared times.
Then my
But then when you take the derivative of that, you have
Negative 2x and 1 minus x.
right. But so are you pulling the negative 2x out too? Also.
Well, hold on. It's like being able to get first thing.
Okay.
Off of that.
Oh yeah, that'd be the 8 Yeah.
Oh, gee,
Like that. Oh, because you were taking that. See, is that part? No, you're taking X. We're not doing X.
Yeah, I also have 1 minus x squared. It's a cheat. So it'll be negative 2x. Okay, we'll do that. It doesn't have like for natural numbers, it's 1 minus x squared. X squared itself. It doesn't make it. So you add it right, just that's nice of 2. Yeah.
Okay. Where do you start? So you can take the derivative of that. It's very complicated. So our goal is to get A over 1 minus R. Is that we can set up a power series for. So how can we adjust that or take a part of that and adjust that to get A over 1 minus R? So you're going to find the power series
Yes,
for that.
take any derivative.
And then what are you going to do to that? To get the power series for L and 1 minus R.
That would be.
No, this is part of the derivative on that. You have to have it so when you take the antiderivative, it's that. You can't change that.
Like,
The x squared, we can get rid of and tack it at the end.
right? Like, you're taking the derivative.
After 2 minutes,
Right, so you have to do, ready to roll?
we're just taking the derivative.
You're just taking the
Negative
derivative
2x,
of that.
right? Yeah, oh, you got that? Oh, just right.
Constantly you're taking the derivative of that.
If you want to, that's 0.
Integrated one.
it's
Like, X.
No, we were negative 2x.
Yeah, I just did terms out next.
That's a variance. So you take the derivative. Yeah, I'll take that, the inverse of that, is that, and then you take that and multiply by R squared.
Well, you
Because
have
that'll
to,
be your
so this,
So that would be.
this.
Okay, yeah, so
power series
like-
of that.
I just,
But we need the
So
power
you're like-
series for L out of 1 minus x squared.
it's a negative 2x.
So what are you going to do to this power series to get the power series for L out of 1 minus x squared? See, this is what, this is the derivative of the power series that you want. So See? This is the power series for the derivative of the one that equals it. So I recommend this way of terms. And do one derivative term by term. Yeah, term by term.
It's just because you
I just said,
you
I got the same.
Why change it up and 1 to 1 plus? Change it to 1 plus. Oh, that's right. So where did you do? You gotta get something that's A over 1 minus R. Where did you do that?
It's the same thing you have.
You need to get something that's related to this, that's A over 1 minus R, so we can set up an initial power series. What are you gonna do?
Oh, is it? Yeah, negative 2 times x to 1 plus 1. Yeah, no, that's.
at the very end, so you're very that would be your x. It's gonna start with x. Where you go and that's the thing. You just don't do that to the very end. It just so happens that these just start with 0, we start with 0.
X to the what? Plus 1, right? Okay, so what I suggest is write out some terms. Write out some terms and then work on the terms. Don't work on this in terms of your next step. Work on the terms.
Yeah. But then I'm trying to get this so I can multiply the x squared back in. Okay.
Plus 1 because we have another x.
Yeah. X to the 2n times another x, so plus 1 more x, good. That's later, right? Giving you a
series on the first line there.
Yeah.
Going from -2 x squared again.
Yeah.
We're going to do negative x squared or negative x.
Yeah, you have to put it.
so is it in the second there?
Well, I don't know.
So where now?
So going from the first series of 2x
Yes.
So
X to the 2n times another x. So x to the 1 plus 1. Good.
Wait, so isn't for the integral on the second line, there's the integral of that very top right, the negative 2x.
Yeah, so the derivative of what we have is that. Then to get that, we're going to take the antiderivative of this. This is what we want.
So we find the series of x.
But we took the derivative of it to get the power series. So now to get the one we want is going to be the antiderivative of that power series. This is what we're after, the power series for this. To get it, we're going to do the power series of this. Its derivative. So then the power series for this is going to be the antiderivative of the one that we found. Okay. Yeah. But we gotta what? So we have to make sure the index is right. So the starting, yeah, you gotta work that out to make sure it's right. But yeah, that's the idea. You're gonna take the antiderivative and then multiply by x squared. Yep.
So like, that's your derivative, right? So now you have to take the derivative of that.
it's better not to combine. It's like it's trying to keep things alive. Because when you take the end and derivative of that, it's just going to be negative x squared to the n plus 1.
Oh, let me stop.
So right in the center, right, there's negative 2x times x squared.
Oh, since it equals
To somehow,
Okay.
so the antiderivative right of that would just be negative x squared to that power plus 1. That's why I got confused when you looked at that, because the one right next to it, I thought it looks, well, it's like it's a antiderivative times 2. But it's just combining that original, so it's not the actual. So, okay. Right, but that's confusing, right? So that's why I'm saying, take the antiderivative of this.
because then the integral of that gives us
You make this, like, that's a
it
really
over 1 minus
hard.
r,
It's confusing.
and then it's like
If you imagine x squared. Right. Okay, so x squared is going to check this is negative, so you know it's negative x squared. And then it's to n in order to the derivative. I have 1. So this is negative. This is
I'm trying to write this out as clear as I can, so I'm not doing this stuff possible.
No, I haven't seen stuff.
So the power series for minus 2x over 1 minus x squared is this. Are we good on that? And but we want the antiderivative of that. Because the antiderivative of that is this thing, ln of 1 minus x squared. So its power series is right here. Power series for ln of 1 minus x squared is here. What did I do? I just did antiderivative term by term. Antiderivative term by term. So I got negative x squared minus 2 over 4 x to the 4th minus 2 over 6 x to the 6th minus 2 over 8 x to the 8th. Agree with that? But then we can also do that. We can just do it once on the general term. So if we want to take the antiderivative of that, what would it be? It'd be negative 2 x to the what? 2n plus 2, but then
over 2n plus 2.
over 2n plus 2. So what's our n going to start at? So we need that first term to be negative x squared. So n needs to start at what to make sure we get this? N equals 0, n equals 1, n equals 2. What is going to, we need for this thing to generate these terms. That's what's going to, that's how you check to make sure you got your n starting correctly. So n needs to start at 0. Because when you put in 0, you get x squared, and you get negative 1, and there it is. So check it, right? So check it. So now n equals 1. If you put n equals 1 in, you should get this term right here. X to the 4th, negative 2 over 4. That's it. We got it. Put in n equals 2. You should get this term right here. So let me rewrite this. So let's see. So, antiderivative, antiderivative, or antiderivative. We're doing antiderivative. And then for this, we're doing antiderivative. So now we have a power series for ln of 1 minus x squared. Last step, piece of cake, right? Last step, all you do is take that power series and so it's going to be negative 2 over 2n plus 2 times x to the what? Almost, you just reversed it. 2n plus 4. And we're going to get negative x to the 4th minus 1/2 x to the 6th minus 1/3 x to the 8th, etc. Okay, looking at the interval of convergence, it looks like it's still going to be between negative 1 and 1. So I was just doing a quick limit ratio test down here. So it still looks like we should be good between negative 1 and 1. So I want to graph these and see if this works, okay? But before we do that, let's talk about what went down here. So I try to do this as clearly as I could to map this out. Any questions? So the key on these is always what derivative or antiderivative can you do on all of it or part of it to get a over 1 minus r? Get a power series that you can do based on the geometric series, right? But since we took the derivative of this and we did the derivative of the power series we wanted, and we're going to take the antiderivative to get the power series for what we started with, ln 1 minus x squared, and then we're going to multiply by x squared. And there it is. Yeah, Louis.
Where did you get for the natural log of 1 minus x squared? Where did you get that -2 over 2 plus 2?
This right here.
No, that one. To the right. Yeah, how'd you get that?
So it's the antiderivative of this general term right here. How would you take the antiderivative of that? We're going to hold on to the -2, and then antiderivative of x to the 2n plus 1. What would that be? This power rule, right? So the power rule, antiderivative would be x to the 2n plus 2, but then divided by that 2n plus 2. You see?
Oh.
So if we were like x to the 5th, and you took the antiderivative, it would be x to the 6 over 6. That's what we're doing. We're adding 1, and then dividing by that new exponent. And that's what, other questions? Okay, so let's graph this. See that this worked. I'm excited. So what is our original function? X squared times ln of 1 minus x squared. So let's just see what that looks like first of all. All right, very good. That's a good. There's that function between -1 and 1. So let's zoom in here a little bit. Okay, nice. Okay. So the blue one is the actual function we were given. All right, and then we're trying to estimate it with this power series, -x to the 4th. So there's the first term. If we just do the first term, that's what it looks like. But then if we do -1/2 x to the 6th, does it get better? -1/3 x to the 8th. So it's looking really good around 0, and by adding more terms, it gets better and better out here at the ends, near 1 and -1. So the last term we got was -1/4 x to the 10th. So you see, it's the more terms you include, the better the approximating polynomial, the power series, does the match of the function. Okay, but only from -1 to 1, or radius or intervals from -1 to 1. Okay, questions on this? Okay, so we're going to move on to Taylor and polynomial. So what we're doing here is we're only able to represent functions that are like geometric series or similar, right? So everything we did, we said it's got to be like this, or a derivative or an antiderivative away from that. So we're limited to very few functions that we can get to look like that with a derivative or antiderivative, or just starting out like that. Okay, so the Taylor and Maclaurin series are a special series that allow us to write any function as a power series. Okay, not just these very rigged ones that are similar to this, right? So everyone we've done so far, similar, one step away from that. But now a Taylor and Maclaurin series lets us write a power series for any function. And so basically we're approximating any function with a polynomial. That's what it ends up doing. We're approximating any function with a polynomial. So this is 8.7. So we can do sine, we can do cosine, we can do e to the x, right? Any of those we would never be able to get it to look like this, right? Natural log functions, well, although we could do some of natural log functions this way, but this is very limiting, right? Using geometric series, very limiting for writing other functions as power series. But with a Taylor and Maclaurin series, we can do any function. And so the Taylor series is this. F of x equals sum. So the nth term, so about x equals a. So when you have a Taylor series, you have a center point, some x value, and then you're going to have it. Oh, it should work for all. And so as you add more terms in your Taylor series, it's going to do a better and better job farther and farther away from a. So a is like the center of the power series, and so you can write any function centered about x equals a as the nth derivative at a over n factorial x minus a to the n. So let's practice. I want you to write out the first three terms. Write out the first three terms of the Taylor series. Should be able to do it. So we see this, and we think what? Write it out. We think what? Write it out. And so this is derivative. This isn't a power. This is the nth derivative. The nth derivative. So what is the 0th derivative? What does that mean? You haven't, no derivatives. So what is it?
1.
Not 1.
0.
Not 0.
Or would it just be the function?
Just the function. It's just the function taken at a. So the 0th derivative means you didn't take a derivative. You got just a function. What does that all equal then? You know what 0 factorial is? It's 1. No, it's 1 by definition. 0 factorial is 1 by definition. So that whole thing is just f of a. So that's probably the hardest term to figure out. The rest of them should be easier. So it's the first, n equals 1, first derivative at a, 1 factorial, x minus a to the 1. Second derivative, 2 factorial, and on and on and on. So it's an infinite series of these terms, and if you add every single term to infinity, that will be a polynomial, and that infinite polynomial will be the same as the function you started with, f of x. Any questions before we do examples? So a Maclaurin series is the nice, easy version. It's all it is a Taylor series where a equals 0. You're centered about 0. So it's a nice place to start. That's all it is. It's a Maclaurin series is a Taylor series where your a equals 0, and so then it's just a lot easier. So it's n equals 0 to infinity. Same thing, but now it's all the derivatives at 0, and then it's just x to the n. So f of 0 over 0 factorial x to the 0 is all 1. So it's just f of 0 plus f prime at 0, 1 factorial x to the 1. Second derivative at 0. One more term here. So where do these come from? We don't have time to talk about it. Okay. So yeah. So it's it's not great practice to just say, here's this thing, and don't show you like where the origin is. I've done that as much as I could all semester, show you where things come from and meanings of things. But these are the derivations of these are complicated. Okay, complex. So we're just going to use it and apply it, okay? Any questions before we do that? So let's just start with a real easy one. Let's do the Maclaurin series first. The Maclaurin series for sine x. So what do we need for that? Well, to do let's do e to the x. Okay, let's do e to the x. So the Maclaurin series for e to the x means that we're going to need all the derivatives of e to the x taken at 0. And then we have it. So this is the rest we just write down, okay? We just write down x to the n factorial. But what makes it different from one function to the next is getting those derivatives, finding all the derivatives at 0, and then you just write it down. Well, what are all the derivatives of e to the x? E to the x. And if we're going to take those at 0, it's just going to be 1. So for e to the x, every one of these is going to be 1. So we can just write it, we're just ready to write it down. E to the x equals, as a Maclaurin series, centered at 0, it's just going to be 1 times x to the n over Why? Because every derivative evaluated at 0 of e to the x, the first derivative, second derivative, third derivative, is just 1. So this power series in other words, 1 plus x squared plus x cubed over 3 factorial, which is 6, plus x to the 4th over 4 factorial, which is 24. If you keep adding terms on forever, you get the exact same function as e to the x. So this is a way of representing e to the x with a polynomial, but you need an infinite number of terms in that polynomial. So let's graph it and see that. So we're interested now in e to the x. Okay, so there's, can you see it? Oh. There we go. So there's e to the x. So here we go. What are the terms? 1 plus x squared. So each time we add a term, you're going to see this thing getting better and better. X cubed over 6, right? Whoa. Plus x to the 4th over 4. 4 factorial. 4 factorial is 24, is that right? See what's happening. Plus x to the 5th. What's 5 factorial? 120. So what's happening? Zoom out. Let's do one more. X to the 6th over, I'll just use factorial. Okay, so every time we add another polynomial, this is on the left side, it's flipping up and down, right? So if we have an x to the 7th, then it's going to flip down. An x to the 8th is going to flip up, but is it going to approximate it for x less than 0? That's the question. I don't see it converging.
The second term is x,
Oh, that's wrong.
and the third one.
Oh, I have them all off. That's why. Thank you. So this is x and this is x squared?
No.
The second one is x squared.
All right. I rushed. 0. So when n equals 1, you get x over 1, and then 2 x squared over 2 factorial. Okay, good. Thank you. So this should be x. So I'll just add it on this side. Plus x. And this should be x squared over 2.
Yeah.
And then do I have it right? Aha. So now it's starting. Okay, let's see, it's a lot better. All right, look at that. All right, so let's take off all of these terms. Let's cut. Okay, so here it is with the first 4 terms. 1 plus x squared over 2 plus x cubed over 6. And now if I add back all those terms up to the 7th term, or 8th term, do you see this is black? See that? That means the red and blue are right on top of each other. And so now the more terms we add, the more it's going to also be correct as you go out to negative. So right now it's pretty close all the way to -2. We keep adding more and more terms, it's going to get more of the graph out to the left as well. Okay, so this is pretty cool. So we can these series are able to reproduce any function using a series of like a polynomial, an infinite polynomial series. And then if we just take, say, the first seven terms, we get a really nice approximation here around 0. For Maclaurin, it's going to be centered at 0. Meaning that they're going to get better and better working their way out from 0. Like it's gonna be exact at 0, and then as you add more terms, it will get more accurate away from 0. So if we did the e to the x, say, and we centered it around x equals 2, then it would look really close at 2, and then it would work its way out from 2 as we added more terms. That would be the Taylor series about x equals 2. All right, so let's do something more interesting. Let's do like sine of 3x. So let's do the Maclaurin series for sine of 3x. More interesting algebraically. That's the only. So Maclaurin series for sine of 3x. So again, we rewrite the Maclaurin series. It's going to be the nth derivative taken at 0 over n factorial x to the n. Again, n factorial x to the n is done. There's nothing to do. So what we need is several derivatives, okay, of this function, of original function, taken at 0. So I recommend making a little chart. Do n value, the nth derivative of our function, the nth derivative at 0. So n equals 0, 1, 2. Okay, so what's the 0th derivative of x? Well, that's just our sine 3x. First derivative then. What's the first derivative of sine of our function sine of 3x?
3 cosine 3x.
Second derivative. Negative. And let's keep, instead of writing it as 9, let's write it as, to keep track of what we're actually doing, we're going to write it as -3 squared sine of 3x. Next derivative is -3 cubed cosine of 3x. Next derivative, positive 3 to the 4th sine 3x. And we're going to keep going like this. Then it's going to be 3 to the 5th cosine, -3 to the 6th, -3 to the 7th. Are we good? All right. And now, what we need is all those values at 0. So from the Maclaurin series, we need those at 0. So sine of 0 is 0. Cosine of 0, 1, but then we have the 3. Sine of 0. Cosine is 1, but then we have -3 cubed. 0. Positive 3 to the 5th. 0. -3 to the 7th. Follow that? So these are our coefficients. Okay, so these are the coefficients. And so what happens with sine and cosine is you only get, in this case, you're only going to get the terms where n is odd. All the terms where n is even are going to just go away. They're gonna, because that's going to be 0. Okay, so we're going to write sine of 3x equals. Okay, so we're going to get 0 when n equals 0 plus 3. Let's do it this way. 3x to the n over n factorial. No, I'll take it back. Sorry. So we want a coefficient times x to the n. So 3 over, what is n now? 1, right? X to the 1 plus 0 plus negative 3 cubed over 3 factorial x cubed. 0 plus 3 to the 5th over 5 factorial x to the 5th minus, we'll do one more, 3 to the 7th Okay, so with these sine and cosine functions, what happens is every other term becomes, for the Maclaurin, every other term is 0. So we can think about how could we rewrite this. Let's see how we do it. Let's start from 0. So could we write a formula that then only generates these terms correctly, right? So when n equals 0, we want to get 3 to the first. And when n equals 1, we want to get negative 3. So first of all, it's alternating. So we're going to have our negative 1 to the n. Right? So when n equals 0, it's going to be positive. So we're going to reform this. So now our new n, this is n equals 0, and this is n equals 1. Let me do this in red. And this is n equals 2, and this is n equals 3. Does that make sense? So we want just the n's to give us, the different n values to just give us the positive, the non-zero terms. So we're going to have an alternating effect. So we have negative 1 to the n, and then we're going to have 3 to the what? So when n is 0, we need 1. And when n is 1, we want 3. And when n is 2, we want 5. When n is 3, we want 7. What is that? 2n plus 1. Okay, and I think that's the same as the factorial that we need, right? We want that same value factorial, 2n plus 1. 1, 3, 5, 7, and then we want x to the same value, 2n plus 1. So by writing it this way, then every n value is significant. There's no 0 terms this way. And we get n equals 0, n equals 1 gives us that, n equals 2 gives us that, n equals 3 gives us that. So this is the power series centered at 0 for sine of 3x. So how can we use this to approximate, say, sine of 6? What would x be? So if we had x equals 2, this thing would be generating the value of sine of 6. We're inputting 2 into this function, and it's going to give us the output, sine of 6. And so we could just rewrite this whole thing, and it would be, what, 2 to the 2n minus 1, or, right? Yeah, so it would be 6 to the 2n minus 1, 2n plus 1. It would be the same as plugging 2 into all these x values, and it would give you an approximation for sine of 6. And you can do that. You can plug the x equals 2 in here, and or you can plug the 2 in here, and that would be giving you an approximation of specifically sine of 6. Okay, so let's, Maclaurin series is the same thing, but instead of x being 0, you're going to have some value, some other value, say a. So let me just give you, let's try one of those. So why don't you find the Taylor series for natural log of x centered about a equals 2. Taylor series for the function ln of x, but centered at a equals 2. You can talk. So the nth derivative. So what I'm trying to show you is you can get a general formula for the nth derivative. What would it be? So when n equals 6, what do you have? Well, first of all, you're alternating, right? It's alternating. So -1 to the, is it n? So here's something also that's happening here. Notice that this is totally different. And it's kind of standalone, right? This doesn't have to do with the pattern that emerges. So what we want to do is we want to just have ln of 2 plus the power series. And then if we have our power series starting with, now make this n equals 0. 1, 2, 3, 4, etc. That n is going to match up with what's happening in the nth derivative. Do you see that? So the first term is just going to be ln of 2 times n equals 0. 1, x minus 2 to the 0 is just 1. So we're going to have that first term ln of 2, and then we'll start the actual series here. So when n equals 0, we're positive. When n equals 1, we're negative. So we can do negative 1 to the n, right? And then what's our numerator? When n equals 1, it's 1. When n equals 2, it's 2 times 1. N equals 3, it's 3 times 2 times 1. What is that? N factorial. What's our denominator? Okay, but that's with this new adjusted value of n, right? So ln of x is going to equal ln of 2 plus n equals 0 to infinity of this thing. Well, so this thing is this part of the Taylor series, right? That's the nth root taken at a. Oh, so is it? Bless you. Okay, but then we're gonna, so that's just, all this is right there is this nth root at a, right? So that whole thing then is divided by what? N factorial, and then times x minus 2 to the n, because that's what we're centered about too. Did you catch it? So we can simplify this. Look, n factorial and n factorial goes away. So we get negative 1 to the n, x minus 2 to the n over 2 to the n. And then we have to add ln of 2. So before, I want to do the graphs. I'm going to do the graphs, but I'm going to make sure that we got the algebra. Makes sense what I did. Do you follow what I did? Anybody have a question? Chat, please. This one right here? So I just looked at what was happening. When n equals 0, I had 1/2. When n equals 1, so it's easier to look down here. So when n equals 4, what do I have? 4 times 3 times 2 times 1 over, 2 to the 5th. I don't have it right. This should be 2 to the n plus 1 right here. This should be 2 to the n plus 1. So I just, instead of finding the actual value, I kept the pattern going so I could see what the pattern is for a given n. So you see, I got it from this. Looking at, say, when n equals 5, I got 5 factorial and then 2 to the 6. So I need 2 to the n plus 1 here. Does it answer it, Martin? Do you follow it now? Okay, so this, then it all, in the end, it's n equals 0, negative 1 to the n, over 2 to the n plus 1, and then x minus 2 to the n. But it's got to be plus, sorry, ln of 2 plus that. So this is kind of a standalone term, right? It doesn't follow this pattern, so we'll just kick it out by itself and then start the series. Okay, there's just a touch more that I wanted to do so you can finish the web work. So what I'll do is I'll just make a little 5-10 minute additional video and tag it on to this video for the class, and then you'll be able to finish all the web work. What's that? Is there a question? So it's due Monday before class, but it's longer. I mean, so but you have time to do it. And then we've got 3 more days and the final exam. It's over. Stay cool. Yep, hand in your seats. Name and date. I need the name and the date. Thursday. Final exam Thursday.